Linear independence. A few days ago, we learned about this innocuous thing called the span, which depends upon linear combinations. Now, the span, together with linear independence, provides a very good characterization of a set of vectors. So, to remind you, the span of a collection of vectors is the set of all linear combinations of those vectors. Now, if you think about it, when I'm taking a set of all linear combinations, I could have, say, the set v1, v2, and v3 of vectors. And the span of this is equal to the set of all alpha v1 plus beta v2 plus some gamma v3, such that alpha, beta, and gamma are real. So it appears that I have, in a sense, three directions here. But that's foolish, because take, for instance, v1 equals 1, 0, 0, v2 equals 0, 1, 0. So here I'm going the x direction, here I'm going the y direction, and v3, I go in the x direction, but I just go twice as fast. Well, the span of v1, v2, and v3 in this case, well, that's the same thing as the span of just v1 and v2, isn't it? This v3 doesn't add any new direction for us. In a sense, v3 was unnecessary. It's extra. Well, that gets us into this notion of linear independence. So what we say is a set of vectors, vi, is linearly independent if this particular sum of vectors only has the trivial solution. All right, so let's think back to my previous example. I had alpha 1, 0, 0 plus some beta 0, 1, 0 plus some gamma 2, 0, 0. I'm looking for solutions to this. Well, this is nothing more than a vector equation. I can rewrite this vector equation as 1, 0, 0, 0, 1, 0, 2, 0, 0 as this. Well, lo and behold, asking whether or not this has trivial or non-trivial solutions is tantamount to solving for our homogeneous solutions to that equation. Very, very important connection. Now, going back to the actual definition, after I've made this wonderful connection for you, does this vector equation have a non-trivial solution? Well, it definitely has a trivial solution, right? We know that this always has a trivial solution, therefore this must, but let's humor it. If I set alpha, beta, and gamma equals 0, well, what would that equal? Well, it would equal 0, wouldn't it? So this does have the trivial solution. Does it have a non-trivial solution? Can y'all think of one? Let's pause for a moment and see if you can. Yep, it sure does. Let's see here. How about we set alpha equal 2, beta equals 0, and gamma equal -1. Well, that's going to give me 2 plus 0 minus 2, which is 0. It'll give me 0 plus 0 plus 0, and then 0 plus 0 plus 0. So yes, indeed, this is a non-trivial solution. Therefore, this system is, well, not this system, I'm sorry, the system where I form 1, 0, 0, 0, 1, 0, 2, 0, 0. This set oops, oh my goodness. This set right here is linearly dependent. Remember how I said that 2, 0, 0 is extra? You could equally view 1, 0, 0 as being extra. Alright, so we've seen what it means to be linearly dependent. Now intuitively, I think you all should see that those are linearly independent. They're both necessary directions in terms of the set. Well, how do we see that? Well, let's go back to the definition. This subset right here I've boxed in is going to be linearly independent if this equation only has the trivial solution. Well, how do you determine if it only has a trivial solution? Well, what you can do is turn it into a matrix equation. That matrix equation is actually an augmented matrix. This right here is what? It is in reduced to echelon form. How many free variables do I have? Well, I have none. And therefore what? That means only has the trivial solution. Therefore, the set 1, 0, 0 and 0, 1, 0 is linearly independent. Alright, we have these three vectors. I left off my transposes here. Y'all will forgive me. Is the set v1, v2, v3 linearly independent? Well, the way we can determine that is converting it to a homogeneous system, because a solution to this homogeneous system will end up being a non-trivial solution in general. So we take this down to its reduced to echelon form, which I'm going to do right now on my calculator. I challenge you all to kind of do it by hand. What I end up with is this. Now, this matrix here, we can see that we have no pivot in that column. Well, what's that mean? That means we have 1 degree of freedom. That 1 degree of freedom, we recall, directly means that what? We have a non-trivial solution to ax equals 0, which is that in disguise. So is it linearly independent? Well, no. No. The set is linearly dependent. Now, part 2 says, if you're linearly dependent, find a linear dependence relation. So what that means is, I know that I'll have alpha v1 plus beta v2 plus some gamma v3 equals 0. That's my equation to test for linear independence. This work I just did all through here tells me this particular vector equation has a non-trivial solution. So that means there's some alpha, beta, and gamma where alpha, beta, and gamma are not all 0. I need to find out what those alpha, beta, and gamma are. The way we do this is we look back at our reduced to echelon form up here. What does this tell us? Well, if I view my original equation here as a homogeneous system, what I did was I formed v1, v2, v3 times some alpha, beta, gamma equals the 0 vector. Well, reduced to echelon form tells me that this says alpha equals 7/3 of gamma, beta equals negative 1/3 of gamma, and gamma is free. Gamma being free, let's set gamma equal to some arbitrary value t, so that our system is alpha equals 7/3 t, beta equals -1/3 t, and gamma is t. Alright, since t is arbitrary, I'm going to choose t to be 3 because I do not like fractions. Well, that gives me a particular solution to ax equals 0 of 7, -1, and 3. Oh my goodness, what have I done here? Let me fix this. There we go, and that's alpha, beta, and gamma. Alright, so I'm saying alpha 7, beta -1, and gamma equals 3 up here will give me a non-trivial linear combination. Let's see that happen. So I'm saying 7v1 minus v2 plus v3, times 3. That should equal the 0 vector. Alright, well, v1 was 1, 2, 3, so that's 7 times 1, 2, 3, minus 4, 5, 6, plus 3 times -1, -3, -5. So that's 7, 14, 21, minus 4, 5, 6, plus, actually let me take my plus and make all those minuses, -3, -9, -15. Alright, 7 plus -4 minus 3, yep, that's 0. 14 plus -5 is 9, and 9 minus 9 is 0. 21 minus 6 minus 15, again, 0. Boom! So what I have here is a nice linear combination. So I want a dependence relation. So what I could say is, for instance, v1 equals 1/7 of v2 minus 3/7 of v3. Or I could have said, for instance, v3 equals some linear combination of v1 and v2. Or I could have said v2 is some linear combination of v1 and v3. The bottom line is I can solve for any one of my vectors in terms of the others, showing that particular vector is actually superfluous. Yes, this set of v1, v2, and v3 from this slide right here, it was dependent. And at the very end there, I was able to solve for v1, v2, or v3 in terms of the other vectors. Alright, now, a non-trivial solution to ax equals 0 corresponds to a linear dependence relation for the columns of A. So that's exactly what I did in the last slide. And so I ask, are the columns linearly independent? Well, asking if they're linearly independent is me saying, all right, let's augment this thing with 0 and see what the reducer echelon form looks like. All right, let me go to my handy dandy calculator and pop that in and see what it says. Well, well, well. Look what we have here. Alright, what do we have here? Well, instead of me telling you, let me just awkwardly pause and let you think about it. Oh yes, that was a nice pause. Okay, so here, let's call that V1. Let's call that one V2. Let's call that one V3. So what we're asking is there a non-trivial solution, alpha, beta, gamma, to this equation, where alpha and beta, gamma would be the vector forming x and ax equals 0. All right, over here, this is my alpha, my beta, my gamma columns. This is telling me explicitly that alpha is 0, beta is 0, and gamma is 0. So in other words, this original system only has the trivial solution. If it only has the trivial solution, then that means the columns of this matrix, this 3 by 3 matrix, must be linearly independent. So the columns are linearly independent. Very easy to see now. Let me go back. Woo-wee! Hold up on this one. All right. Theorems. The set V, that's the vector V and nothing but V, is linearly independent if and only if V is not 0. Okay, and that's of course the 0 vector here. That, I hope, is clear. We'll prove this in class otherwise. All right. We go up to a 2-element set. The set V and W is independent if and only if V is not a constant multiple of W. I challenge you to sit down and prove this on your own. Otherwise, I'll prove it in class. And the final theorem. A set of 2 or more vectors is dependent if and only if at least one of the vectors is a linear combination of the others. We did this a minute ago. That is all this theorem here says. If you're dependent, I can take one of my vectors and write as a linear combination of the others. And notice that all 3 of these theorems are biconditionals. So these are pretty powerful theorems. Careful. This is one of the biggest hiccups in linear algebra. It's a comment about the last theorem. The last theorem says I can take one vector, or at least one, and write as a linear combination of the others. Note this does not say that every vector is a linear combination of the others. That is not the same thing. So be careful. And how do I say to be careful? I note that one of those coefficients could be 0. So for instance, when I take alpha V1 plus beta V2 plus gamma V3, let's actually throw an extra one there, delta V4. Let's hypothetically say that that vector equation has the solution alpha, beta, gamma, delta equals 1, 0, 0, negative 1. Now, if that is the solution, then what I'm really saying here is V1 equals, actually make this a 2 V4. Because the weights on beta and gamma are both 0, it's impossible for me to solve for V2 or V3. So it's going back to here. We're not saying that every vector here can be written as a linear combination of others, just at least one. So be mindful. Slide that if I have 2 vectors, they're independent if and only if they're not multiples of one another. All right, I give you 2 vectors here. Let's describe their span. All right, well, their span is completely determined by the reduced echelon form. But do we really need the reduced echelon form? The only way the span of 2 vectors could be essentially one-dimensional is if one of the vectors was a linear combination of the other. Let me repeat that for you, because this is an important concept. We're taking the span of 2 vectors. At best, this is going to span some kind of plane in some kind of dimensional space. In this case, we're in R3. So therefore, we really can't talk about a plane in space. Now anyways, the only way this will not give us a plane is if one of these vectors is a linear combination of the other. This is going back to the theorem on the... Okay, so be careful. I'm only using 2 vectors here. That's why I can use that theorem. All right. Now, is 160 a constant multiple of 310? Well, let's think about that. In order to go from 3 to 1, I'd need a 1/3 weight. To go from 1 to 6 with a 1/3 weight would force this to be a what? A 2. No, a 1/3, my lord. So, what's that mean? That means it is definitely not dependent. In other words, V and W are linearly independent as a set. So what's the span? The span must be a plane. If it turned out that W was a multiple of V, and oh my goodness, I just realized something. I'm talking about V and W, and I have U and V here. Oh my goodness, then where's W? Oh my, oh Lord. Okay, all right, we'll come back to that. Let's just pretend that this is U, and I mean V there. And let me go back. All right. If V was a multiple of U, then we get the span to be a line, assuming that U is non-zero. All right. Now, number 2 here. Let's try to salvage this problem. I figured it out. All right. What I want is W is an element of the span of U and V, where U and V are as above. That's if and only if the set UVW is linearly dependent. Okay, now we have something we can work with. So let's prove this direction. So what we have is W is in the span of U and V. Well, that means there exists alpha and beta in R such that W is alpha U plus beta V. Well, I can solve this thing for 0, namely alpha U plus beta V minus W equals 0. Does this have a non-trivial solution? Well, yeah. Even if alpha and beta in this case are both 0, the coefficient in front of W is -1. So I know that alpha, beta, -1 is not 0. Therefore, that's a non-trivial solution, and therefore my set here must be dependent. The other direction. The other direction assumes we have a dependence relation. So that means there exists alpha, beta, and gamma, not all 0, in R. Let me write like this. Not all 0, such that alpha U plus beta V plus gamma W equals 0. All right. For the sake of argument, let's look at this. What if gamma was 0? Well, if gamma was 0, what would that imply? That would imply alpha U plus beta V equals 0. Well, what's that imply? Well, at least one of these must be non-zero, and we both know that U and V are non-zero, so I guess that would have to be that U is a multiple of V. Well, if U is a multiple of V, that means the set U and V must be what? It must be dependent. But we already showed up above that these two vectors, U and V, are independent. So that's impossible. So gamma cannot be 0. So therefore, gamma is not 0. Well, if gamma is not 0, we can solve for gamma W. Like so. And then gamma not being 0 means we can divide by gamma. That's negative alpha over gamma U minus beta over gamma V. And there we go. We have a bona fide dependence relation. So it's in the span of the other two. as you can see, because I've written W as a linear combination of U and V. Okay, suppose a set of vectors has cardinality greater than the number of entries in each vector. All right, so what I'm saying here is we have a collection of vectors with this going on, like 1, 0, 0, 0. So how many entries? It's 4 entries. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Right now, if I were to close this up with another curly brace, that set would be independent. Now let's do 0, 0, 1, 1. Well, I have more vectors than I do entries in any given vector. That forces this set to be dependent. Another way of thinking about this is this second clause. If the matrix consisting of the columns formed by this collection of vectors is wider than it is tall, then the vectors are dependent. So what I have here is basically the identity matrix with 0, 0, 1, 1, if you think about it, right? Well, that is going to be a wide matrix. How wide? Well, it's a 5 by 4 matrix. Therefore, it must be dependent. Another one is any set containing the 0 vector is going to be dependent. That should be pretty clear because the weight, let's call it Z, in front of the 0 vector, I have my linear combination there, I can put any number there for Z, and therefore it's always going to be a non-trivial solution. Now, let's determine by inspection if the given sets are dependent or not. This requires zero calculation. The first case, if I formed a matrix out of this, it would be a fat matrix, wouldn't it? Well, that means it must be dependent. This next one, what's wrong with that collection? Well, it has a 0 vector. Therefore, it is dependent. This next one, can I see them as multiples of each other? Because the first thing you should check is when you have a 2-element set, you ask, is W a multiple of V? In this case, it's impossible for W to be a multiple of V. Why is that? That is the opposite sign of that, that's the opposite sign of that, and that's the opposite sign of that. Are these opposite in sign? No, they are not. Therefore, they will be independent.